Hello! The main issues of the research work of the business unit Component Safety and Lightweight Construction is the assessment of the deformation and failure behavior of structural components. And I've got one example right with me. This is the rear wall of an airbag container. And this has been fixed to a testing machine and loaded onto impact. And we see a quite complex fracture behavior picture. If we have a close look at the component, we'll see that the material the component is made of is a fiber reinforced plastic. Actually, is a polypropylene with glass fibers, the so-called LFT material. So why do we deal with deformation and failure behavior of such components in the first place? It's because we want to know about loading limits under which neither too large deformations nor failure occurs. So we want to establish those limits. And normally in the procedure, standard specimens are taken from a component to get information for material models, and with those material models a complex behavior is simulated under different loading conditions, so the limits can be simulated and established. Not always we have component or parts in a large number or in a sufficient number, so it's often the case that we use so-called component-like specimens. They do exhibit features of components such as notches like here or ribs underneath here, and again these tests are made for validation of your material model and your damage model, in which information out of standard tensile tests or other tests are used. So, and I'm going to show you right now what can be seen or observed in such a test. This is the specimen, and it will be loaded under actual loading direction. And we start the video, we'll be seeing the loading of the specimen and areas within the specimen which turn gray, which is an indication of micro-cracking and micro-damaging. And in the end, we see that fibers are pulled out, and this is of course also has to do with interface properties and behaviors. So we do a series of tests, for instance, in order to investigate the difference between quasi-static loading and high-velocity loading. And in the next slide, you see the difference quasi-static and dynamic of a fracture surface at the end of the test. And the expert will see that under quasi-static loading conditions we have a smaller kind of deformation areas in the fractured region, which leads to a more brittle behavior, deformation behavior, opposed to what we see in this fracture surface, which has been generated under dynamic conditions. Here the matrix behavior is much more ductile and larger deformations take place. So this leads in the end to a different amount of energy absorption due to higher forces or deformations that will occur under these conditions. But not only for automotive applications, micro tests are important, which I'm going to show you next. What we can learn from such component tests is to be seen in a video like this. I'm going to start this now. You see two specimens which are loaded under impact or compression loading. In this case, the loading has a velocity of 1.35 meters per second, and the video gives us information about the global fracture behavior of the component, which is quite typical here because it's a little bit a mixture of the material behavior and deformation or fracture triggered by geometry. So not only things that we see on the surface are interesting, also what is happening inside the material is of interest, and this can be seen here. We now see again two videos at the same time, and this time you see thermography analysis or measurements during the test, and they indicate, especially in these regions where the temperature rises, and this is done under high-speed conditions with a high-speed infrared system. And you see under these high loading velocities the regions which are heated up actually in the material. So and the heating up of the material, the quick heating up of the material, is a measure for the energy which is dissipated by damage. And if we want to have more insight and more information on what's actually happening in those localized regions, we need to use the micro-specimen technique. Yeah, I'm showing you another micro-specimen. Looks very similar to the one I've shown you before, but there are differences. Well, the length is the same, 3.5 millimeters, but it's much smaller, about 100 microns in width. And the major difference is that we use these micro specimens for another type of testing. You see here this test setup. This time it's not loading in one direction, well, slowly or fast, but it's doing a cyclic loading, which we use to be able to make assessments of lifetime or fatigue behavior. During the loading, we again observe damage behavior and development via a video camera, and I'm going to show you right now what is to be seen if we observe the specimen itself, but also what we can do in simulation to describe the behavior numerically. And in the simulation we have the material models and try to simulate exactly what is happening in the real specimen, and that looks quite good in this case. The damage initiates in the same region of the specimen, in the real specimen, as in the simulation. So what we have to take into account in the model is the matrix behavior as well as the interface behavior between matrix and fibers. But as we say, behind every colorful picture there's got to be a powerful material model, and this slide shows some details, overall rough details about what we put into the material model. And you see that we use representative volume elements and accumulate damage in the volume elements to be able to describe the deformation behavior of the whole specimen. So that shows you, hopefully, that well, depending on the question you like to answer or the prognosis quality you like to achieve, it's very useful to look into the microstructure, not only of the fiber reinforcement materials, but in metals as well.